Hey, what's going on, guys? Kamekigans here. In this video, we're going to be programming user-defined graphics in 652 machine codes on this device, which is the Arduino Nano based Kin1 emulator with an extended output capability. So it's going to have LCD display instead of 7-segment LEDs. And we're going to be writing the program on this piece of paper. We're going to be drawing the sprite that was supposed to be displaying in this tiny little cells, then encoding it to binary, then to hexadecimal, then input here, and then write a simple driver program to actually display character here on the LCD screen. So if we're interested, without further ado, let's actually start. Okay, so the graphical LCD screens like this one I have here, so 16 columns, 2 rows, and it's like there are tiny little pixels there. So it supports up to 8 user-defined characters, and we can draw whatever they are, whatever that fits 5 by 8 pixels. So let's actually draw the area for that. So starting from the top left corner, we have 1, 2, 3, 4, 5 like this, and 1, 2, 3, 4, 5, 6, 7, 8 here. So here is a rectangle that represents a single character on the LCD screen. And now we can just fill the cells here to represent the pixels being kind of turned off, and we can leave blank those that we want to keep kind of turned off. So yeah, sorry, those that are light up would it be like filled. Those that are not light up, those just leave blank. So I was thinking, what can we actually draw here? And I thought that maybe drawing a chess pawn might be on the card. So it doesn't really matter what exactly would I be drawing, but I don't know, something that I can actually draw in pixels. So let's just try to draw this pixels one by one to represent a chess pawn. So here I'm just filling those squares where I want the pixels being light up eventually, and here like this, okay, and probably here as well, and then maybe something like this goes. All right, and finally the solid bases down below. Okay, so it's arguable whether this looks like a chess pawn or not, but that's the best thing I could have came up with so far. And now what we need to do next is actually to encode this sort of a thing into binary. So now you might be wondering why we have only 5 but not 8 bits in the long in a row, and that's the reason because the first 3 bits are actually used in order to encode the index of this user-defined character, so from 0 to 7. So these bytes are preserved for this. So for every row, we just add those zeros as the preserved bits. So we're not going to be touching those bits ever. So we just fill them like as they are. And then here, the next 5 bits would be representing this sort of a graphic. So all the blank squares should be zeros, and the filled squares should be ones. So we have 0, 0, 1, 0, 0, and let's put it in. So 0, 0, 1, 0, 0, right? 0, 0, 1, 0, 0. Okay, 0, 1, 1, 1, 0. 0, 1, 1, 1, 0. Okay, same thing here. So 0, 1, 1, 1, 0. Then 0, 0, 1, 0, 0. 0, 0, 1, 0, 0. 0, 0, 1, 0, 0. And here as well, 0, 0, 1, 0, 0. And here 0, 1, 1, 1, 0, and all the ones down below. Okay, so far so good. So from now on we can convert this binary numbers into the hexadecimal. So here we have the binary data, and here we'll have the hexadecimal data. And the hexadecimal data already could be input here, right? So if we just like visually split this in like 4 by 4 elements. So the hex digit is represented by 2 digits always. So I mean, like, well, at least when we're inputting this into the into this Q1 emulator. So we need to now convert this 4 bits so this 4 bits into hexadecimal, and the first digit would represent the most significant nibble, and this 4 would be represented the least significant nibble. So this is going to be 0 and 4. Okay, so this bit is worth 4. So again, like, for those of you who don't remember this, so this bit worth 1, 2, 4, 8, and same for this guys as well. So it would be like 1, 2, 4, 8. So, and then we just take a digit from here and take a digit from here and put them together. So this is gonna be 0, okay, and this is gonna be 4. Okay, so this is gonna be 0, and this is gonna be, so it would be 15, like F, but minus 1. This is gonna be E, right? Yes, this is gonna be E. This is gonna be E as well, so 0, E, and this is gonna be 0, 4, and this is gonna be 0, 4, still 0, 4, again 0, E, and this is gonna be, sorry, not 0, this is gonna be 1, sorry, 1, F, like this, because we have 1 here, and all the ones represents decimal 15 or hexadecimal F. So these are the values here that we actually want to input into our device in order to make sure that they get encoded properly. And now let's write a simple program that would actually display this pawn on the LCD screen. So I have a custom implementation for user-defined graphics on this device, and I'm using the address of D017 in order to encode, in order to invoke the function to create the user-defined graphics, right? And it takes arguments in X and Y registers. So X register is the index of, it might be either index 0, 1, 2, 3, 4, 5, 6, 7, depending on what kind of number for this user-defined graphics we're going to be assigning. So I'm going to be assigning the value of 0. And also in the Y register, we need to store the pointer to the very first byte, to this byte basically, that starts like where the user-defined graphic definition actually starts. But since I'm gonna be putting this into the 0 page, so both X and Y registers would be equal to 0 because well, 0 index, like the very first one, the very first user-defined character, and as far as this bit, this byte is going to be in the address of hexadecimal 0000, the very first byte in the 0 pages. Still, the Y register is still going to be equal to 0. So if I just say, like, so this here we have the 0 pages, and then we will have 04, then 00, 01 will be 0E, then 00, 02 will be 0E. So I'm already kind of writing the program here, and 0003 is going to be 04, and then 0004 is going to be 04. 0005 is going to be 04, 0006 is going to be 0E, and 0007 is going to be 1F. Okay, so far so good. Okay, so the next thing to consider, so these are the 0 pages, so we can actually keep them separate. And now the program itself. So I think that it's a good idea to start the program at 0200, right? So I just skip some place for, yeah, actually I need up to 3, so yeah, somewhere. So now I'll start my assembly here. So the very first thing we need to do here is to reset both the X and Y registers. So I want to say like LDX and want to load the immediate data of 0 here, and then the same with the LDY. So the reason for doing this is very simple. So X register equals to 0 means that we want to define the very first user-defined character. Y register equals to 0 means that the source of this user-defined graphics data is available at the address of 00, right? So the next thing, I have a specific address, D017, which is mapped to the functionality of creating the user-defined character on the LCD screen. So here I just need to say STA and set the value to, well, this could be not STA, this could be STX, STY, whatever, and no matter what is in the A register. So this is just a custom implementation that is specific to this device. And D017. So it's literally enough just to have X and Y registers being initialized properly. And then when we invoke the writing to this specific address, it would already automatically create a user-defined character for us. And from now on, the only thing that we need to do is actually to print this onto the screen. So now we can say LDA and the immediate data of 0, and in this case this 0 is sort of a ASCII character, but instead of printing the ASCII character, which it actually would be printing the user-defined graphics that we've defined here instead, right? So, and then we want to say STA to the address D012, and this D012 is another address specific to this device where the printing of the LCD character to the screen is mapped to. And that's pretty much all about it, basically. So from now on, all we need to do is to actually input these codes into the computer. And if I did everything properly, then hopefully it kind of works. Yeah, but one more little thing. As far as we don't really have an assembler and just using the pen and the paper, we also need to encode. Yeah, I forgot the most important thing. We need to encode this into 6502 machine codes. So the opcode for LDX, the immediate data is A2. So here I can say A2, and then 00, that's the data that we want to load. So A2, 00. For LDY, this is going to be A0 and 00. For STA, it's an opcode AD, STA to the absolute address, and not D017 but 17D0 because of the little endian byte order in 6502 processor. So 17 followed by the D0. Then opcode for LD immediate data is A9. So we say A9 and 00, and finally STA to D012, so it's the same thing, so AD12 D0. And if we now input this the character data into the 0 page at the address 0000, and then if we input the program into 200 hexadecimal, and then if we go back to the 200 hexadecimal and run the program, then we should see a tiny little point here on the very first kind of cell of the LCD screen. So without further ado, let's actually give it a try. So go into the data mode because I want to input this guys here, and let's go. So 04, and then so we select the address 000. We do input the value of 04. Then the next address 001. So we want to input 0E. Let's go for it, 0E. Then again 0E. Okay. Then 04. 04. 04, so 6, again 0E, and 7 is 1F. No, what did I say? 1E, should be 1F. Sorry, yeah, it's 1F. F. And here we have 1F. Okay. Now let's get back to the data mode and make sure that we did input everything properly. So 04, 0E, 0E, 04, 04, 04, 0E, 1F. So far so good. So now we go to 0 to 00, and it's time to input our data. So let's go for it as well. So I say, oh, sorry, 0 to 0, 0. Yeah, I forgot to go to the data mode. So here I have A2, 0, 0. Okay, then A0, 0, 0. So now we did initialize the X and Y register. So far, so good. And then we go to 8D, 8D, 17, D0. All right. Then A9, 0, 0. Then AD, 12, D0. Let's go back to data mode and 0 to 0 to 0, 0. Let's verify things. So A2, 0, 0, A0, 0, 0, AD, 17, D0, A9, 0, 0, 8D, 12, D0. Yeah, so far so good. So we can already run this, but well, I know that it won't work properly currently because it just runs the program, and since the next byte is 0, 0, which stands for break instruction, 652 assembly, it would just drop back to the key monitor, and you won't really be able to see the pawn there. I just know that already, but just want to show you that it's not a pre-coded thing, and I'm really doing this from scratch. So let's go back to the dressing mode, and then we'll just add the infinite loop to trap the processor, so it would be just displaying this for forever, literally. And here, let's go and run. So this is the run button. So like it goes, but it then just drops back, and that's, yeah, it's just executed the bytes, but didn't show anything because we just returned back to the key monitor. So it's not really what we want to do. And now let's adjust the addresses. So A2, 0, 0, A0. So this is address 0 to 0, 2. This is the A0, yes. So AD is 0 to 0, 4, and 0 to 0, 7, and 0 to 0, 9. And starting from the address 0 to 0C, we want just to jump to this address. So the jump instruction is for C, and in the little endian order, this is going to be 0C, 0C, 02. Okay, so here we want to jump to the address of 020C, so loop forever, literally. Okay, so here I'm going back to the address mode, so sorry, to the data mode, and here I can say for C and 0C, nope, 0C and 02, and going back to addressing mode, and let's check this out. So this is 020C, so for C, 0C, 02. So far so good. So from now on, if we run this program from 200 hexadecimal, it should actually now be working properly, because just the processor gets trapped and it should be displaying this pawn forever. So let's try this. Let's check if that works. And yeah, starting from A2, and here we go. And as you can see, guys, here we have well, it's really hard to say whether it looks like a pawn or not, but if you have a closer look, it really looks like what we have here. I'll now try to adjust the camera slightly a little bit just to better show you this. So, yep. Okay. And yeah, so you can see that really kind of exactly what we just tried to kind of like draw on the screen. Okay guys, so this is pretty it from my side. Thanks for watching. Until the next time, and take care.